the ideal gas law. So we've talked about some simple gas laws. There's at least one other, Gay-Lussac's law, that we didn't talk about. But we can take all of these and combine them into one law. And if you're interested in looking at the derivation of that, I'd be happy to show you. Most of you are not interested. This is the bottom line, what you need to know. That's the ideal gas law. PV equals nRT. Some people call it PIV-NERT. So the pressure times the volume is equal to the amount of gas times a constant times the temperature in kelvins. And that constant is the ideal gas constant. What value it has depends on the units that we're using for pressure and volume. Temperature is always in Kelvin, N is always in moles, but pressure and volume can be different. So the one we're going to use is 0.08206 liter atmospheres per mole Kelvin. So we're going to use atmospheres for pressure and liters for volume. You will save a lot of time if you memorize the gas constant. So we can get all of these simple gas laws out of the ideal gas law. And I want to show you here how you can derive whatever equation you need. Let's see what's coming up. Okay. So PV equals nRT. And under a different set of conditions, PV is equal to nRT. Any gas, any amount of gas, any temperature, any pressure, essentially, this is true. The pressure volume is equal to nRT. So if I take this ideal gas equation and I divide it by another one, is it still equal? I divided this side by green, PV, and I divided this side by green nRT, but green nRT equals PV. They're the same value. So I took one and divided by the other. Now you can't use colors all the time. So let's put some numbers in here. P1, V1, call this 2. One's up here and 2's in the bottom. I'm not going to put a 1 or a 2 on the gas constant because it's a gas constant. It doesn't change. So if R is always the same, it cancels out, right? I can cancel this out because R divided by R is 1. Now what if I had this situation where I had constant temperature and constant moles of gas? The amount of gas in moles wasn't changing. Then N1 would be equal to N2. It's not changing. So that would cancel out. And I said, so we're looking at constant N and T, just as a for instance. So I'm saying the temperature isn't changing. That means whatever it is, T1 is equal to T2, and that cancels out. What is this side equal to now? 1. Everything canceled out. It's equal to 1. So I could rearrange this and say P1 V1 equals P2 V2. Here's Boyle's law. Poof! Out of the ideal gas law. You can make all of the simple gas laws and one that's called the combined gas law, where you've got 3 things changing, by doing that. So that's what I would encourage you to do rather than trying to memorize those different ones. Because remembering which one has the fractions and which ones don't, it can be confusing. Any questions? Let's do an ideal gas problem. An 8.50 liter tire contains 0.552 moles of gas at a temperature of 305 Kelvin What is the pressure in atmospheres and psi of the gas in the tire? Now we have a title up here that tells us we need the ideal gas law. What if there's no title? How do we know? When you, pardon me? Yeah, so we've got all four of these numbers, but we don't have anything changing, right? In the simple gas laws, you've got a volume changing, a temperature changing, something's changing. This is a static deal. We have a tire, and it's just sitting there, and we've got this information. You can still use the table and write the numbers down and identify them, and what you'll find is that you only have one row. And there's your clue. Use the ideal gas law. So I'm just going to go through the numbers and write them down. 8.50 liters. Well, liter is a unit of volume. That's my volume. And then it says 0.552 moles. And what letter is that equal to? N. And then I have a temperature, tells me temperature, 305 Kelvin. So that's T. And then the question is, what's the pressure? Pressure equals question mark. They want ATM and PSI. I don't have any ones or twos, nothing's changing. Ideal gas law. PV equals nRT. So I want pressure. I'm going to rearrange this. And I'll see that the pressure equals nRT over V. Well, so we need R. R is 0.08206 liter atmospheres per mole Kelvin. The units on the gas constant tell you what the units of your other variables have to be. The volume has to be in liters, N is in moles, T is in Kelvin. Pressure, when we solve here, will end up with atmospheres. If I had this volume in milliliters, it would be good to change it to liters before I stick it in the equation. So, N is 0.552 moles. And then R, stick the whole thing in here, 0.8206, all the units, liter atmospheres per mole Kelvin, times the temperature, 305 Kelvin, and all of that is divided by the volume, 8.50 liters. Before you bother doing the math, check the numbers. So moles cancel with moles, Kelvin cancels Kelvin, liter cancels liter, I'm left with atmospheres. 0.552 times 0.08206 times 305 divided by 8.5 equals. So pressure equals 1.6. See, we should have 3 sig figs. So 1.62, and then write down a couple more, 54 atmospheres. So I'd say the pressure is 1.63 atmospheres. How do I convert that to PSI? Yeah, 1 ATM is equal to 14.7 PSI. So I take my number times 14.7. And that's going to give me 23.89289, blah, blah, blah. That'll also have 3 sig figs. That'll round to 23.9 PSI. This is the relationship between atmospheres and PSI. I don't expect you to have that memorized on an exam. I'd give it to you on a homework or something. You have to look it up. It's actually 14.69, but. For this one, you need to have both answers because it says, what is the pressure in atmospheres and PSI? It's asking for two answers, so you better give two answers. Any other questions? Yes? You do not need to memorize the conversion factor. The only ones you need to know are 1 atmosphere is 760 torr, which is 760 millimeters of mercury. Let's do another one. What volume does 0.556 moles of gas occupy at a pressure of 715 millimeters of mercury and a temperature of 58 degrees Celsius? I look at this problem, I see that there's no change occurring. I'm going to use PV equals nRT. So I'm going to write down all these variables and identify them. 0.556 moles. Well, that's N. The pressure is 715 millimeters of mercury. It tells me that that's a pressure, but the unit should also clue me in. And then temperature, 58 degrees Celsius. So I'm going to be using PV equals nRT. What am I solving for? Volume. Volume equals, we don't know. So if I want volume by itself, I have to divide by P. If I do it on one side, I have to do it on the other side. So volume equals nRT over P. Well, what's R? 0.08206 liter atmospheres per mole Kelvin. I should look at these units and make sure that all of these things have the correct units before I plug them in. Otherwise, things aren't going to cancel out. Moles is okay. Millimeters of mercury, not so much. I need to convert this to atmospheres. And all of these pressure conversions can be done in one step. So I multiply by atmospheres, I divide by millimeters of mercury. This is one you're supposed to know. 1 atmosphere is exactly 760 millimeters of mercury. I'm going to erase this equation because I didn't leave myself enough space. So 715 divided by 760. How many sig figs? 3. 0.940, keep 2 extras, 79 atmospheres. That's my pressure. Is 58 degrees Celsius okay? No. I need to add 273.15 to that. $331.15. And that has the last significant figure is in the ones place. So volume is equal to nRT over P. So my N in moles, 0.556 moles. R, 0.08206 liter atmospheres. I hate it when I do that. Per mole Kelvin. Temperature is 331.15 Kelvin. all divided by the pressure, 0.94079 atmospheres. Double check that the units cancel. Moles cancel moles, Kelvin cancels Kelvin, atmospheres cancel atmospheres. And so I'm going to end up with my volume in liters, 0.556 times 0.08206 times 331.15 divided by 0.94079 equals 16.0597 liters. We'll express that as 16.1 liters. Any questions?